graduated from here almost exactly 20 years ago. So it's really great to be back. The Stony Brook is a place really has I have great memories here, and at Santa Barbara, which happens to have the same initial as Stony Brook, so cannot yeah. So I was working under Detlef, and he is always very kind and encouraging to his students, as you will see. And okay, so after I graduate, before I leave to Boston, so actually I found this memo I still have. Actually, this is the memo is you maybe not see clearly, but it's a good. Before I left Boston, he left this message in my mailbox. It's really very encouraging. And I thought this maybe will be my great gift to my daughter when she goes to college as a same message. So actually, because you see the picture you saw is when they took their big son to visit Harvard, he was admitted to Harvard. He was in the Harvard class. But so I only remember the small son for this picture one. So when he mentioned, I forgot about the big son. Anyway, but I don't have the picture when they visited Santa Barbara. So actually, the title will be really the Ricci curvature for a smooth metric measure space. And I learned and studied Ricci curvature from my thesis, working on a great problem that will give me. And Ricci curvature become my passion actually afterwards. So I'm still really addicted. Okay, the material is contained in these two papers which are available in the archive. First is joined with Will Wiley, it's here, and the second is joined with Jeffrey Case and Eugene Shi. She also graduated from here, so she is a postdoc at Santa Barbara right now. Okay, so first let me start with smooth metric measure space. I think it sounds a little funny, so what are they exactly? Okay, so when I say this smooth metric measure space, it's really a Riemannian manifold such that the measure is changed. Okay, so Riemannian manifold, f is a function on the manifold, and so the measure is changed by so it always comes with a canonical measure. So, but it's now you're adding a conformal change. So really, this is just a Riemannian manifold with conformal change of the measure in this case. Okay, so really contains Riemannian manifold. Okay, so actually, measure was never one of my favorite things. So why I want to study this? Okay, so motivation. So that's why. I think I really did not. The motivation for studying this place was really because it occurs naturally as measured Gromov-Hausdorff limit. So I won't give examples, so really convince you guys. Okay, so how does it exactly occur? Okay, if we take, let's say, two manifolds which are compact, as for simplest, let's equip with, so it's a product space with this Walker product metric. Okay, F again is function on the base. Let's say F is just a fiber. Okay, so if we take this Walker product metric and stick with the epsilon, when epsilon goes to 0, so the fiber is clasped going to a point of it. Okay, then or the usual measure is going to okay, so it's going to the base, and the general measure if we take is going to 0, so it's not very interesting. But instead, if we take this so-called renormalized Riemannian measure. So what this is just a product measure, a product walk with Riemannian measure, but divided by, you take a unit ball here with respect to a fixed, say, reference point. So this is just the usual Riemannian measure divided by, so renormalized. So that it will not be 0. So we can write it. the usual base metric, but with this conformal change. Okay, so recall, usually we say compact space, metric space with measure, converges to another matrix with measure. Okay, so this is a metric space. If you converge usually in the usual Gromov-Hausdorff sense, and in addition, the measures converge. So what do we mean by measure converge? This is the usual Greek topology. Namely, if you have sequence of function on the sequence, converge to a function in the limit, then the integral of the measure also converges. Okay, so that's what we can define. Okay, so now we see in this limit, we have this usually measure like this conformal change. Well, this have this m here, so we can rewrite it if we want to normalize. So as epsilon going to 0, I rewrite it. This to be just the negative f, the one we introduced before, and I make smaller change in here in the sequence. Okay, so this kind of smooth metric space really occurs naturally as Gromov-Hausdorff limit with respect to measure. Okay. Other reasons we'll talk about later, but this is really mainly that I'm interested in. Okay. All right. So then, in this case, of course, well, for this kind of space, then how we want to define the Ricci curvature set? That's the thing I always interested. How we can define curvature because the measure is changed, right? So well, we want to have some connection between because this is a limit. So it must be related to some kind of curvature in here, right? Okay, so if this is just a walk product, we can compute whatever formula we can use as either embedding or submotion. Let's say if we use submotion, O'Neill's formula, you can compute the Ricci curvature in the base direction, m. Okay, and it will be the Ricci curvature of the origin of the m, but modified with Hessian of m and this product depends on the n in the fiber function m. Okay, so this motivated us that define Ricci curvature using this is a motivation for. This is not originally how it works. That's equal, but I'm putting it so that's how to motivate. We'll define the so-called, the name is called Bakry-Emery Ricci tensor as just so Bakry-Emery Ricci tensor for smooth metric space of certain function is a usual Ricci curvature Hessian m and this. Okay, so we really just because if we want to see from sequence, that's exactly the Ricci curvature of the base of the walk product. So this is really a family of Ricci curvature with a parameter m. M is a positive, also could be infinite. We can take. So if m is infinite, this term will be just a 0. All right. Okay, so simple observations about this new Ricci curvature. So when it's infinite, later on I'll just write as Ricci to f without the infinite. So it's just a Ricci plus the Hessian of f. And notice that this term is definite sign. It's so therefore, when it monotonely changes, the bigger the m, this bound below this will be the bigger because what you subtract is going to be smaller. This has definite sign. So automatically, if for finite m you have this Bakry-Emery Ricci lower bound, it implies infinite. Okay, so for Ricci lower bound, the finite seems to be stronger than the infinite one in this case. Okay, so those simple observations about this Ricci curvature. Okay, well, you said what other? This actually a notion of Bakry-Emery, it really goes back very early. There's there's lots of study. I mean, go back and recently it's probably not so organized. So there's many other motivations for studying this. So I will list some of them here. Well, one motivation is this is some kind of generalization. If I take f to be constant, this is just a usual Ricci curvature we're familiar with. Okay, so. And if we look at this Quasi-Einstein equation, actually this name may not be really good. That's so fun. Okay, namely, if we take this Bakry-Emery Ricci tensor equal to multiple of the metric, it's like as I call it the Einstein case, right? So we call this if we look at this equation, this has very nice geometric interpretations too. Okay. So first is, if in the case when n is infinite, then this equation is really exactly the gradient-Ricci-Solidal equations, which is a very interesting Ricci-Solidal studying the theories of Brook. Okay. Now when n is finite, let's say I'm assuming it's finite and also it's positive integer. In this case, then this equation, okay, this Einstein equation, actually exactly what corresponds to this Walker product, which we did before in the beginning. If you take this Walker product metric with fiber here, fiber has to be Einstein and the Einstein constant has to be determinant. It's anything. Then this whole space is just the usual Einstein. Okay, so what saying that this quasi-Einstein metric is equivalent to saying a high-dimensional space when this is integer, it's just an Einstein. So it's really another way of studying Einstein metric, walking product. So this is in physicists, they are interested in Einstein metric case. Okay. So this observation, we made this observation using this Pinking's work. They were studying walking product Einstein metric. Okay, another reason for studying this kind of rich cultures I'm interested is that lofty learning and independently stone have this rich culture lower bound for non-smooth metric space. And if we specialize that bound to smooth ones, the one we just discussed, then it's exactly that same curvature. It's equivalent to this curvature is bounded below. So it has nice correspondence. Okay, so are you all motivated? Okay, so some more reasons, but I'm not going to talk about it. If you're still, you're welcome to look up. All right. Okay. Hopefully we are motivated. Now then, okay. So once we have a natural question we can ask about is what kind of geometric topology result for the usual Ricci curvature can be generalized to these big Bakry-Emery Ricci. Actually, before I was saying Bakry, and then said it should be Bakry. Anyway, I might use both. Okay. Well, actually, so when n is finite and infinite, these things have different stories. In this case, when n is finite, actually, you can summarize many geometric topological results for the usual Ricci curvature can be extended directly to this new Ricci curvature. Okay, this is work by Bakry-Ricci and Lott, Bakry-Ricci and other people, and many. Okay, so what's the reason? I'll just give one example, show it, and I'll show another later. And one way you can see this is from this Lott's work. Namely, if there's some special constructor, this gives you the idea. If it's compact with Bakry-Emery Ricci tensor, so this actually only makes sense when n is positive integer, but still gives you a really good idea. If it's bounded from below by lambda, then again we take the same walk product metric with the sphere, or actually any Einstein metric with constant equal to 1. Then this walk product actually, as we explained before, it's not surprising that it will have the usual Ricci curvature bounded from below. Okay, so any result you're looking for geometric topological result, in some sense, you can just go to a higher dimension, right? Which will have the usual bound, and once from here go back. Of course, not all of them, but then topologically, sphere is a very simple topology, should not interfere. Okay, so that's one way to see that when n is finite, or at least a positive integer, you can just go direct. Okay. We'll see. There's another way later to show you this. So what about n equal to infinite? In this case, what we can do? Okay, n infinite is so clearly we cannot multiply by infinite dimensional space. So does not seem to work. So what do we expect? Well, before we speculate anything, let's look at some examples so we know what we non-trivial one. Does not have the usual rich curvature, but has this Bakry-Emery Ricci curvature. So first example we can look at is actually look at the high quality space. Fixed any point, and if I take the function to be the distance function square, distance, so it will very big. When x going to very big. And this is a very convex function. The hashing of these functions is strictly positive. Not only that, when you put in the, okay, so this rich curvature is negative, but since the hash of this is so much positive such that if you add together, it becomes strictly positive. Okay, so you see that if you have very complex functions, you can add, you can multiply by any constant, then the curvature will be very, very big, as positive as you want. Okay. So that's different from the usual curvature. So from this sense, then Meyer theorem and Detlef Gromoll's isometric splitting theorem, it does not hold. We have many lines here, but does not split isometrically. And the manifold is not compact. Okay. Although the curvature is uniform from okay, what about other results? Well, the very useful result we mentioned before is the volume comparison theorem. So if we Bishop Gromoll volume, if we look at this, let's take the Euclidean space and take the function to be linear functions, then hashing is 0. So the rich curvature corresponding to the usual rich curvature is 0. But if we look at the volume, well, if we want to look at the original volume here, this is very big. Now, maybe more natural to look at the so-called F volume, mainly because that's the measure we consider. Even look at this measure because the exponential, this is linear, right? So this will have exponential volume growth. So it may not be polynomial anymore, even with the Ricci bounded from 0. Okay. So this example shows that direct generalization does not hold when n is infinite. Any questions? Yes.
When m is infinite, do you take the product with an infinite dimensional space? Or?
Right. Okay. So in a constructed example, yes. But then I can define this rich curvature just abstractly without this thinking about the example. Okay. So we still can define this here, the rich of n. So without this term, it's just a rich hashing f. So this the rich is infinite will be just usual rich curvature modified by hashing of f. That will be our new curvature. So it does not have this Walker product interpretation, but you can just purely consider this rich curvature, see what happens. Right. I guess, yes, because we have to work in order to make it has to be infinite dimensional, that's why it does not work anymore. It's something very defined. Okay. Right. Okay, so maybe that's the end of the story. Something does not hold. But if we look at a little bit more carefully, is that actually many results do extend if we assume something about the function f. Namely, f is bounded or gradient f is bounded. Because if you look at common examples, those function f, they're all going to be very big in one way or another. Okay, so before I state the result, let me introduce some notations. Okay, now because our measure is make this conformal change with respect to measure, we can consider the Laplace operators, right? Now, we want Laplace operator to be self-adjoint, then we need to consider this modified Laplace, because otherwise it will not be self-adjoint with respect to this measure. It will be the usual Laplace modified this first order term, so that this will be self-adjoint with respect. So this is a Laplace we're going to consider later on all the time. So I want to introduce the notation. And similarly, in curvature measures the change of the geodesic sphere, right? Now our measure changes, so we also this will be also the usual curvature and by because EF, right? modified in curvature, the new measure. And with these changes, it happens also nicely. Before we have that Laplacian distance function is a mean curvature, and with most change, they also satisfy these relations. Okay, so Laplacian distance function and mean curvature also connect very nicely. Okay, so the volume, you will also consider this volume is a new measure, is F, and last. This will be the mean curvature of the geodesic sphere in the model space. So later on, because of the change of dimension, I want here, H is a curvature in the model space, K is a dimension of the model space, because they might change of the dimension. Okay, that's it. Okay, so this is joint with Wiley. Okay, so yes. One of the really fundamental results for Ricci curvature is mean curvature or Laplace. Comparison depends on who you talk to, but it's really the same thing because Laplace distance is the mean curvature, right? Okay, so we extend this to the near Ricci curvature. So Bakry-Emery, if the Ricci curvature is bounded from below before, okay, we said in general we cannot expect any comparison. Now, if we assume the gradient of F in the R direction is bounded from below by a constant, okay, then this modified mean curvature you can compare to the, okay, if I don't write any dimension here, then it's just always same dimension as the manifold we talked about. Okay. If it's different, I'll write it. You can compare to the usual model space, the mean curvature. Instead of less or equal to 0, this is less or equal to 8. It is a constant here. Okay, so maybe I should stick to the usual mean curvature comparison. So, mean curvature comparison, or really the Laplace comparison, is that the mean curvature is bounded by the mean curvature of the model space, or of the analysis in the Laplace of the distance function is bounded by Laplace of the model space. Okay, in this case. So this is always less or equal to the model, and in here, so we say instead it's less or equal to 8. Okay, so this is one version. Another version is if we assume F, the absolute value is bounded instead of the gradient F. So there are some minor assumptions when H is positive. In this case, the mean curvature is less or equal to the model 1's, but the dimension has to change. The model 1's dimension is n plus 4k. Okay, so k is bound here. The matches is a constant. Okay, so the dimension has to increase in this case. In both cases, in these both versions generalize if the usual mean curvature comparison, namely in the usual case, we can take F to be constant, for example, here, then this A will be equal to 0, and that gives the usual mean curvature comparison. Or actually, in the usual, we can take K to be also 0, right? And yet, this assumption of curvature does not depend on constant. So when K equal to 0, again, this gives the usual mean curvature comparison. This will be the usual. Both of them. So, okay. So in that case, that this assumption. Is there any questions? Okay. So this is really the key in many comparisons. Once have the Laplace mean curvature comparison, then okay. So naturally, we can get the volume comparison. So version of volume comparison. So instead of, say, this ratio of the big ball with small ball is bounded by model, now we have a fact of the expansion, okay, instead of the usual volume comparison. So because the fact that the curvature also measures the rate of change of the area of the geodesic sphere. Okay. And we can formulate the other version similarly. In this case, then the volume, but it will be the dimension of the model space again has to be changed and modified. So the ratio is So what does it give us? Really, something is, notice that when the function f is bounded and the Bakry-Emery is greater or equal to 0, then the volume growth has to be polynomial volume growth here, right? Because even if it's any constant k, still has to be polynomial. As example we showed before, without any assumption, it could be exponential growth. I still don't know. From here it doesn't. It's about optimal, this constant, this here, 4k. I actually, it would be really good to find some non-trivial examples showing this has to be go up by how far is that?
Is there any characterization of the rigidity case or the equality case? Can you say?
Yes, there are some calculations too, right? Yeah, then this f has to be some, there are some functions of that. Right.
That's number 4.
Okay, maybe in the proof. Okay. Let's see, but we see that in the curvature, right? Yeah, okay, well, so once we have that for, all right. Okay, so let me give 2 applications maybe in the proof. Let's see if we can see that. Okay, so Laplace comparison, volume comparison has many applications actually. Okay, so one of them, I'd say, can think about, because everybody all know my theorem. I said in general it cannot be true. My theorem can be proved by curvature, although you can do variation. But if we use curvature comparison, we can also do the Meyer theorem. So if it's uniformly bounded, function is bounded, then it's also the diameter is bounded. Again, when k equals 0, that's the usual diameter bound we get. So use the curvature Laplace comparison. Then, of course, most famous one is Detlef Gromoll's isometric splitting theorem. Right? Once you have Laplace comparison, then all these Laplace will constitute Laplace alpha carries over. So if it reaches non-active, f is bounded, then it's split, and f has to be constant. Actually, very interesting. Afterwards we found these results proved by Lichtenwitz back right after Detlef Gromoll did the original theorem. Well, he did not use these names and stuff, but he was considering this culture, which plus tensor mentioned to us, right? And then after I gave the talk in November, he said, and this paper actually he already did. I don't know why. Well, actually in complex geometry they always add up actually, and he did this result.
An example of the topology of the first theorem?
This
topology?
Pardon me?
Do you have an example of the topology of the first theorem?
The post? No, I don't have it. Not triggered. No. Yeah, that would be very nice. Okay, another of the actually that it's enough to this. You already isometric split if you can just add this bounded from above, one side from above. In this case, actually you can say it's only linear along the line. So this is by family side afterwards. Okay, so as I said, this splitting theorem and Laplace comparison or volume comparison, as usual, has many applications. I really would not do any more applications. Either you already know it, I'll just copy over. It's not, or if you don't know it, you have to learn it. So I'm not going to talk about it yet. Okay. Instead, let me give a little bit idea of the proof. Sorry, I missed one point. Okay, about how much access estimate. So Mike already mentioned what's the access in the morning, and then so the k is basically the change. When k equals to 0, that's exactly the original condition of this access. Okay, all the Yeah, I copy again. All right. Okay. So that's again. This one has many applications. Okay. So those all these applications once have that. Okay. So now let me give just an idea of the proof. Actually, what I'm going to start is kind of philosophical thing, not really go direct. Okay. Just about studying manifolds, Ricci-culture bond in general. So this. Okay, a very important formula for studying manifold with Ricci-culture bond is a Bakry formula. Okay, this really go back very basic. For any function on the manifold, you have this equality, Ricci-culture up here on the right-hand side. This can be seen as Laplace gradient. Here is gradient Laplace. So when you change the derivative, what occurs? When you take the trace, that's what Ricci-culture occurs here. So this plays a very important role. And how we usually use them in this. Most of the time we have Ricci-culture low bond, right? Here is bond from below. And this looks very hard to control, but this has a definite sign. And you can always usually use Cauchy-Schwarz to make it to also Laplace. So then all C here Laplace, they all match it. Very nice inequality. And this inequality actually characterizes Ricci-culture low bond. So we said if you have Ricci-culture low bond, then for any smooth function you have this inequality. Now for a manifold, Riemannian manifold, if this is true for any smooth functions, then Ricci-culture has to be bounded from below. So Ricci-culture low bond is really, in some sense, all here. Well, one interpretation is in this inequality. Okay, so it looks like in here. So naturally, how we want to study is a Bakry-Emery Ricci-culture. Okay, so then we want to change the Ricci-culture here to the Bakry-Emery, and then maybe change the Laplace to the F Laplace, right? So that will be most natural thing to do. And one can do that. So this we introduced before. And actually it was still very nice in some sense. It's almost same as the Bakry formula before. So we have the new Laplace here, right? And this Ricci-culture exactly matches, this Ricci-culture matches except this has one more term here. Okay? So it's very, very similar to the Bakry. Really looks really good in this case. Okay, well actually the actual term here, this has definite sign. So when n is finite, we could use this term combined with Hessian, like the Cauchy-Schwarz inequality together. We can combine them together so that this also becomes Laplace of F. Okay, so what we use, really we want this, all of the matches, otherwise we cannot. So if I look at this, this is exactly the same Bakry inequality we see it before, which characterizes Ricci-culture low bond, right? So this we have, this is the second way I was mentioning before. When n is finite, see once you have this Bakry inequality, you have everything, all Laplace comparison, they all come out naturally. So this is when n is finite. This is just exactly the Bakry inequality we had before. Okay. Okay, so therefore, yeah, from here we can see very quickly, when it's finite, you have low bond, then you have the Ricci-culture. Okay, here we see that the why m is coming because of the m plus n. So we see we need to modify the dimension. We also saw it from walk product, you need to go up, and from here you also see. Okay. So when finite, this is another, this works for, does not, walk product, you have to be positive integers, is for any and finite. Now let's look at this case when it's infinite. Okay, when it's infinite, actually looks like, so this term is gone, this is 0, right? Okay, so if we look at it, looks like even neater. On the other hand, we have trouble applying it because Hessian of F, if you use Cauchy-Schwarz, it will be regular Laplace. And this too is Laplace F, they do not match. So usual comparison does not apply. Okay, so you cannot really, you will actually stuck here for a while. You know, we can be so beautiful, must be, but then we're stuck. Okay, so well, we have worked several ways. Actually, finally, so now it's the start of the proof. So this is just a general thought, maybe what we went through or something. And as a proof we found, actually, last proof we found, well, I hope this is really simple. It's just a start on the yo-yo Ricci inequality. Okay, so like you prove the yo-yo mean curvature, this might get a new mean curvature kind of comparison proof. You start from the yo-yo Ricci inequality. Okay, so this is the idea of the proof now. And look at this function I call SMH, which are really the coefficient of the Jacobi field of the model space. You know, we would consider the sine and r and the h group. Okay, so from the model space, you have this equality and this inequality, and combine a little computation shows that if I multiply this mean curvature by this sign, this coefficient, you know, look at some with the model space we have equality and so on. Okay, it's skipping some steps, but mainly the computation shows that the derivative of this is less or equal to, now, okay, here I use the Ricci curvature, Bakry and Ricci curvature low bound, Bakry, and they become this term. Okay, so if we integrate, we say this is actually this kind of the error term is given by second derivative of the f. Right? So if f is constant, this is, because this is a positive term, this is just a usual curvature comparison. Okay, so this is kind of, and this way this way of proving the usual curvature comparison makes the generalization really just straightforward. Now in order to control, I just all need to do is here do integration by part. Once, then I can apply the gradient f assumption twice, just the f assumption. So skip that. Okay, any questions? So from this on, you can integration by part. Any questions? Okay, right. Now I want to do the second part of the talk. Okay, so the question is, what about equality case? So we look at manifold with lower bound. The Bakry-Emery is bounded from below. What about the equality case? Well, we already mentioned this. We can define this as quasi-Einstein. So this is a generalization of Einstein in some sense. And okay, so just to motivate again, when f is constant, this is just the Einstein case. And we will call this is a trivial case. Okay. Well, sorry, it's not really true. But when f is in some sense not new, not twisted examples. When m is infinite, this is a gradient rich solid equation, and the case I'm going to mention most later on. I mentioned when lambda is positive, this usually refer to a shrinking soliton because if you run the rich flow, it will be going to a point if lambda is positive. Okay. So then what kind of okay, so yeah, when it's positive integer, the Walker is the Einstein. So we mentioned of this before. So what kind of question we can talk about for equality case? Okay. Well, we can ask, you know, because for Einstein metric, say what kind of property? So then what kind of property of quasi-Einstein metric? Or what is there? So when is it rigid? Rigid means it's trivial. F has to be constant in some case. So there's no new. Then if it's not rigid, what are the non-trivial examples you can ask about? Okay, so quickly go through some previous work in this direction. In lower dimension, compact rich soliton is always trivial, namely it has to be Einstein. Okay, so this is by Hamilton IV. And in high dimensional, well, in this one, the Y tensor is always 0. So in high dimensional, if you assume Y tensor is 0, then this many works, similar result of work. The work by Gibson, Wiley, me, and other people in this case. So they're also similar motion in high dimension. When lambda is less or equal to 0, the lambda is like the Einstein constant we showed before. for when less or equal to 0 compact manifolds, then there also has to be trivial, and the F has to be constant. There's no non-trivial example. So this also happens to be, Lichner was already in the 0 case, he already did that. And IV for M is infinite, and King for M is finite. Okay, so there's, for example, rigidity result for rich soliton with symmetry. It's by Gibson and Wally. And for compact shrinks with positive curvature operator, these are trivial. So by Bowman and Wilkins. Yeah. So those, okay, from look at here, looks like all I say is trivial. Right? So let's see, is there non-trivial examples? Okay, well, there are. So I want to show you really very, very special examples. Okay, look at this example, famous Gauss soliton. The Euclidean space takes a function to be just a distance square, then it sets out this equation. So it's a shrinking soliton, which is also Einstein. Okay? Like you have non-trivial function f satisfy this equation. Okay, so actually, this is the only non-trivial gradient soliton, which is Einstein. Right? And what about the other cases? So you observe this example, taking hyperbolic space with the Walker product, and if take m, take function to be n times t, then this is also we call it case. Okay, in this case. And okay, later on we prove that this is essentially the only non-trivial finite n quasi-Einstein, which is also. So this is Einstein. In addition, is also quasi-Einstein. Okay, so those really okay. So here, but if we look at it, all these examples non-compact. Okay, and non-compact. Lots of things I said is trivial. So what about compact examples? Compact and non-trivial examples. Okay, compact when m is infinite. Suppose the non-trivial example is by Heusel and Charles. It connects on CP2 with negative CP2. And when n is finite, actually we were looking for examples, and then we find this already done by physicists. They have, actually this was a question raised by Bessie's book about constructing compact non-trivial compact Einstein metric, which are Walker's product. So this gives examples. There are S2 bundles over Einstein space. Okay, so then we say n equal to 1, there's no compact case. Okay, then
It's not, however, there are none.
there are none. There are no trivial. Yeah. Okay, so actually we will, after we found this paper, we were very excited to want to use this method to construct shrinking solutons. Then after we done, actually, Denisi and Huang already posted this paper. They construct a lot of in the end, the construction is very similar. Okay. So to comment in this, all the known really non-trivial example when m is infinite are scalar. Okay. And this one, when m is finite, they are non-scalar. And actually, there happen to be maybe some reasons later on. Okay, so these are all known examples of results. Okay, so what we did. So this is joint work with Jeffrey Case and Eugene Xu. So in some words, to summarize this, we extend several results about which soliton, which is m infinite, to m finite, or we include m infinite and finite. Okay. So this shows some similarity between finite m and infinite m. Okay. And also, we showed that in the scalar quasi-Einstein case, when m is finite and n is infinite, it's very, very different. Okay, so let me, any questions? More precisely, what do I mean? Okay, so some property we proved, for example, is for quasi-Einstein, if lambda is positive, okay, so like it's a shrinking case, then the scalar curvature is bounded from below, okay, by this. So these are already known as the n is equal to 3 case. When lambda is 0, the steady solid term, and I is scalar curvature, sorry, I is scalar curvature. Scalar curvature is constant, then has to be Ricci flat. And when lambda is less than 0, then the scalar curvature has to be bounded in between. Okay. So these results are actually when infinite is already done by Peter Wiley. It's really after Peter Hom did a talk about his work, and we said, oh, we can do the finite case. We thought it was much easier because the case when n finite, the lower bound is much stronger than infinite. But in the equality case, you know, this equation is a lot more messy, actually. It's very, very messy. The equation we deal with was much, because the equality, the other one is much neat. Okay, so yeah, when n equals 1, this has to be that wise. There's no natural. All right, so the other thing we did is a rigidity case. We said when it's a trivial in this case. So I referred before, if it's a quasi-Einstein metric, which is also Einstein, then it can be characterized. So topologically it has to be Rn and has to be Wolf product metric in this case. Okay, so that's just the using equations. You can basically it has to be very quickly. Then we showed that any two-dimensional quasi-Einstein metric, so finite n, it's also trivial. So when this n is infinite, it's already done by Hamilton already. We proved it for finite. Okay, so I thought the interesting case is a Taylor case. If it's a Taylor quasi-Einstein, then actually for n is finite, like this, then the manifold has to be split. This is a Riemannian product split. The one part and 1 is just the Einstein, usual Einstein. And 2 is two-dimensional quasi-Einstein. So basically, if it's Taylor and quasi-Einstein, basically it's just Einstein. The only thing non-trivial is about two-dimensional. You put something which is not trivial is two-dimensional. In two-dimensional compact case, we said it's trivial, there's nothing. So therefore, for compact ones, there is no trivial Taylor quasi-Einstein metrics. That's why, well, all the examples are not Taylor. For infinite, I guess, there is no examples you can construct. Then this is really, somehow, this may be just a coincidence. In the n equal to infinite case, all the compact, no example happen to be Taylor. So, but maybe it's just that they don't have a way. Okay, so in the end, maybe, maybe we'll skip that, few questions. Maybe I can have some great advice here that the purpose I did in the talk. Okay, so notice that for compact with measure, notice that from what we showed, all the topological restrictions are similar, right? We proved this because if it's compact, the function f is automatically bounded, right? We have this comparison f needs to be bounded, but for compact one, f is always bounded. So we have all the comparisons. So once you have the comparisons, the topological restriction is similar. So then you can ask, if you have this metric with greater or equal to 0, does it already has another cause? Now the same metric, there could be negative examples. In the beginning said, what I did, is it just an empty set? Is it already the usual Ricci curvature is greater or equal to 0? Okay, there are definitely examples, even in Ricci solid case. On the other hand, we can ask, does it have another metric such that it's a regular Ricci curvature? Then, yeah, that would be really good. So what's the key difference? Okay, so somehow we only did with two-dimensional showing it's trivial, and we couldn't do it for three-dimensional. Or even more general, you can do the high-dimensional with 0, 1, 2. No, we haven't done that. we haven't really. Now the question I haven't solved very clearly is example of non-trivial one. We can make trivial one shrinking. Okay, that's all.
Are there any other questions?
Other obstructions, just like for Einstein, other obstructions for this code?
There's no parallel. No, it's like the unions is a kitchen top, union top. No, people try it, but none of them really good. No. Yeah, this apple really mess up. The kitchen top, yeah, very good. No, people definitely study it. They don't have really need lots of extra assumptions.
Bounded F?
Yes.
Aren't there any examples of the maximum volume?
No, I don't. Well, natural example we can look at is Heisenberg group. Those are, have regular Ricci, does not have a metric with a regular Ricci curvature low bound. So can you construct an F function made with mu Ricci curvature? This will the volume at least. One may not be optimal, but at least you say the volume is bigger than the dimension. Yeah, I even don't have that example. So that was the first thing I thought of. The Heisenberg manifold. Can you make a function? That's yes.
So, in answer to the last question, this is sort of in a trivial direction, since there definitely are non-Kähler Einstein.
Just the product. Yeah, the trivial one.
Well, there are also things like the page metric on teaching book at one point, which is a conformally Kähler but not Kähler Einstein metric.
Right.
So that that certainly is it is a non-Kähler shrinking.
Sorry.
But
Yeah.
F not constant.
Yeah. I mean,
So
really,
the
not
curious
trivial.
thing is that on that particular manifold, for example, there are then two different things. There's also a soliton metric, which
Right.
is F non-constant,
Right.
which is Kähler.
Yes.
And
Yes.
It's not,
Right.
It's a curious situation. I mean,
Yes.
maybe there are more on spaces that are just that simple.
Right. There could be another metric. Yeah. Yeah. I don't know.